So this next section is, there's going to be two different formulas, but I'm going to start with the double angle. It's actually double angle and half angle, but I'll do 7.3 with the double angle. If you kind of notice here, right, double like twins, because the double angle, the double angle comes from the sum and difference. And the idea is, if these 2 degrees or radians are the same, when you add them, you'll get 2 of one of those angles. Hence the double angle. Hence these 2 little twins. I'm just saying that the 2 angles are the same. Hence we would get cosine. It comes from the sum formula. It would be cosine 2 theta. And if you remember the sum and difference formula for cosine, just the sum one, it's cosine alpha cosine beta, and then it's minus sine alpha sine beta. But what happens is that these 2 angles or radians are the same. So if 2 functions are multiplying to have the exact same argument, that's just going to become cosine squared theta minus sine squared theta. And to continue with the theme of manipulating identities, if you notice, I can manipulate, and be careful, this is not cosine squared plus sine squared equals 1. This is minus, so it's slightly different. But that doesn't mean I can manipulate cosine squared to be 1 minus sine squared theta, which will give me a second version of this identity, which would be 1 minus 2 sine squared theta. Or I can rewrite sine squared as 1 minus cosine squared using the Pythagorean identity. And it'll give me a third version of this double angle, which would be 2 cosine squared theta minus 1. So we have one version here, version 2, version 3. So they're all equivalent to each other. It's just being able to manipulate to what you need. And now for sine 2 theta, we'll have 2 sine theta cosine theta. And again, it's coming from the sum formula. For sine cosine, I'm going to do tangent, which gives me 2 tangent theta all over 1 minus tangent squared theta. Now let's see an example using these identities in different ways. Right, so one, which we just got finished doing at the end of the other example, which is verifying identities or proving identities. I'm going to start with the left-hand side, right? And like I keep saying, I could have just as easily written this on the right-hand side and then this 4 cosine x minus secant x on the left, and I could have started on the right. And I'm choosing to start on the side that I feel I have more to work with, which in this example is the left-hand side. Now, this was tricky at first glance. There's not really anything that's guiding me to what this next step is. And sometimes that happens with this verifying identities, that there's no clear step for the next for what you should do next. Now, because we're just learning the double angle, sure, there's a version of sine cosine, but it needs a 2 to be a double angle, but it's close, right? Here is a triple angle, so then that feels that I can't use sine 2 theta. And sometimes it really is just you creating almost a trick, I would say, truly. So, for example, sorry, it copied this part as well. I'm just going to cut it. And this trick is this. So I'm going to try to get in here and work with this problem. And the trick is writing, just because we got finished doing the sum formulas, I'm going to write this as sine x plus 2x over sine of x cosine of x. And then here, this allows me to see my double angle, and this lets me use my sum and difference formula for sine. And I could expand that to give me, using the sum and difference, will become sine x cosine 2x plus cosine of x sine of 2x. Because if you remember, the sum formula for sine is that it alternates. Sine and cosine get each one of these terms, and then they swap. So sine got x first. On the second term, cosine gets x. On this first term, cosine gets 2x. On the second term, sine gets 2x. So they switch. And this is all still over sine of x cosine of x. Now, this is where we can finally see, okay, here are my double angles. Right, so that the big first step is showing how we're going to use the sum formula for sine. And then second is seeing that double angle at first glance. And another separate step is trying to deal all this together can get tricky, because I do notice maybe there's a way to simplify some of these additional factors with what I have in my denominator. But we've done this trick before where you can actually separate the terms from numerator. So I can create two separate terms because I have one single term. Even though there's multiple factors in the denominator, there's only one single term, because terms are separated by plus or minus signs. Factors are separated through multiplication. This allows me to simplify my sine of x in one of the terms and cosine of x in the other. But now I'm going to use my double angle identities to expand this further. Now, there was 3 different versions of cosine 2x, but seeing that I have a cosine in my denominator, I am going to expand. I'm going to use cosine squared x minus 1 version with that cosine in the denominator. Plus, there's only one version for sine 2x, and that's just 2 sine x cosine x all over sine of x. And here, at least in the second term, we can simplify our cosine of x. Now here you might, our sine of x. And here you might want to simplify cosine of x, but that minus doesn't allow you to do that. When you only have, but once again, when you have only one term in the denominator, this is always a good rule of thumb that you can always separate it, the numerator, to have that same denominator. Oops. Cosine of x plus, and we still had 2 cosine x remaining. This allows me to simplify one of the cosines. And then I have 2 cosine plus 2 cosine. That's going to help me simplify to 4 cosine of x. And I have this 1 minus 1 over, negative 1 over cosine of x, which at one point you want to start looking back at what were we trying to get to, right? That right-hand side is minus secant x. So that I have a minus, and I know, wait, 1 over cosine is equal to secant x. And now I have got into my right-hand side, and that is what I was looking for. So again, just showing how we can use various identities. Some can be a little more challenging. Some have these quick tricks separating the argument, right? This is separating the fractions. There's all these additional steps that you can take. Now, this actually comes more from, I would say, section 7.5, when we start dealing with more equations that involve applying these new identities. So this example, the trick is noticing, wait, sine theta, cosine theta, that is almost my double angle, except the fact that I have, because normally we would, if this was equal to 0, we can use our zero factor property, but being equal to negative half makes it a little trickier. But if I take this equation, multiply both sides by 2, and again, the idea is to use the identity of this being my double angle. So this all simplifies to sine 2 theta equals negative 1. And this is very similar to an example we did for 7.4, when we had an argument that was not just theta, but we still have to think about, when does this general argument, I know I have to solve for theta, but I know in general what radian or degree will give me what I'm looking for. And then I was able to substitute for that radian I created to solve for that problem. So in this example, I can do the same idea by just essentially allowing this to be, let's say, sine of A equal to negative 1, because then I have to think, okay, what radiant will give me, and really quickly, I'm only looking for the solutions between within this one interval from 0 to 2 pi. So I know sine is equal to negative 1 at one place and one place only, and that is 3 pi over 2. Before we were adding our 2 pi k, because I can get to that same position an infinite number of times, and that 2 pi k accounted for getting back to that same position over and over again. But now I'm only looking between this interval, and sine is equal to negative 1 only once in that interval. So that gives us that 2 theta has to be equal to 3 pi over 2. And then to actually isolate my theta, I divide both sides by 2, leaving me with, well, here for some side work, I would have to take 3 pi over 2 and multiply by the reciprocal of 2, which would be 1 over 2, giving me 3 pi over 4 as my answer to this original equation. Now to do one more to not make this example very long, we can take this equation, cosine 2t is equal to cosine of t. Here, the other example, I condensed it to my double angle. This one I'm going to expand my double angle to become 2 cosine squared t minus 1 is equal to cosine of t. Now, if you're wondering, why would I rewrite it in this version? That's because I already have a cosine in this equation. I wouldn't want to rewrite it as cosine squared and sine squared, or 1 minus 2 sine squared. I'd rather write it as 2 cosine squared minus 1 because I want to keep it uniform with the other function in this equation. Now, doing this helps me rewrite this. If you recognize, this starts looking almost, right, to give you guys a hint, this almost looks like saying 2x squared minus 1 equals x, which I can rewrite as 2x squared minus x minus 1 equaling 0, which looks very similar to a quadratic equation that can factor to 2x plus 1 and x minus 1 equals 0. And I can do the same thing with my equation by becoming cosine squared t minus cosine of t minus 1 equals 0, which will factor into 2 cosine of t plus 1 and cosine of t minus 1 equaling 0. And the zero factor property allows me to rewrite this into 2 separate equations. Cosine 2 cosine t plus 1 equals 0, or cosine of t minus 1 equaling 0. Now, isolating my cosine, I would have cosine of t equals negative 1/2, or I have cosine of t equaling 1. Taking my problem here to not make it super long, I'm just trying to find versions of t, and remember, I'm only within 0 to 2 pi interval. So if I draw this unit circle here to help me think about when is cosine equal to negative 1/2, well, that has to happen in either quadrant 2 or 3, just because that's where my x-axis is negative. And I know cosine is 1/2 at pi over 3. So that also has to happen at 2 pi over 3. So that's where my negative answer will be, right? Because I have, once again, 1, 2, 3, 1, 2, 3. When I say 1, I really mean 1/2. When I say 2, I really mean square root of 2 over 3. When I say 3, I really mean square root of 3 over 2. Cosine pertains to the x, so 1 is my 1/2 I'm looking for, and that happens here on this end and happens down here. This is my 2 pi over 3. Let's not forget 1, 2, 3, one more. This is my 4 pi over 3. And if I make another cross here, I'm trying to find when cosine is 1. That happens right at the beginning here. So that's just at 0, because on this end, this is when it's -1. And I'm not including 2 pi just because if I include 2 pi, then that would also be another place where cosine is equal to 1. Now, these are not general solutions. These are solutions just for one, just within that interval, 2 pi over 3, 4 pi over 3, and 0. And in some cases, some teachers prefer you using set notation to illustrate your solution set. I'm okay with either or, but I think it's good to just show how that came to be. But like I said, these identities either allow us to practice more proving, more verifying, or allow us to do a wider range of equations. Like I said, this is probably coming more from a 7.5 section. I won't really cover 7.5. I will give you assignments from there because this type of problem comes from that section. So practicing more equations, but this is more focusing on using identities and not thinking much of a general solution, but maybe solutions within a single interval. Thank you.